Okay, our next speaker is Alan McLeay from the University of Strathclyde, who will be talking about small covers of big surfaces.
Thanks very much for the invitation and for coming today, wherever you are. Yeah, so this is joint work with Ty Ghaswala from Waterloo. And before I begin talking, I should say I'll define what a small cover and a big surface is later. These are my own informal words. Okay, and also I should maybe apologise because there's not much group theory in this. Well, I mean, there is, but you have to look at it from a distance. So I've adorned all my pictures with groups to make us all feel better about that. So by a small cover, I mean a finite-sheeted cover. And first of all, let's just look at, and it's always covers of surfaces. I always think about surfaces. I generally study mapping class groups and things like this, so this is why I look at surfaces. So finite-sheeted covers of compact surfaces. Let's start there. And I've got very limited imagination when it comes to these things. So what I generally just think of is regular covers, and when I think about regular covers, I just think about cyclic covers. And when I just think about cyclic covers, I just embed a surface somehow in 3 dimensions and act on it and think about the quotient space. So for example, this first picture here, you can kind of insert this central red axis around this genus 4 surface and rotate it 2 pi by 3. And this covers a genus 2 surface where this red circle, sorry, the blue circle has 3 pre-images as a disconnected pre-image. And the green curve has a connected pre-image. So already that's quite an interesting, phenomenon to look at. And then you can extend this example by adding an extra leg onto your, like a fidget spinner kind of thing. You just add an extra one on, and now you have the group of deck transformations is Z mod 4, but it's the same idea, and it covers genus 2 surface, and you can go on forever until you have a genus G surface covering genus 2 surface, where the deck group is ZG-1. So somehow all these surfaces, all these closed surfaces from genus 2 up are related, and they're all related through these curves. And they're similar in many other ways if you look at the topology of these surfaces. So the last example of a compact cover, a finite cover of compact surfaces I want to look at is now we introduced some boundary. And here it's the same thing, there's going to be some axis of rotation around this thing until you flip this over by pi, and now you have a cool phenomenon of a surface of genus covering a surface without genus. Okay, and that's going to be useful later on. And the important thing here is the boundary components. If this didn't have boundary components, if this is just a torus covering a sphere, it would be branched. There are lots of 4 branch points, and the boundary escapes the branch points. So this could be the whole talk. You could draw pictures of covers. But I could maybe ask a question, which is if S1 and S2, even better, are compact surfaces, when does there exist a K-sheeted cover between them? Can you always just cook up some kind of cover like this? And so you think about this for a while, and you come up with 2 necessary conditions you're going to need, first of all, in your surfaces. The first one is that there's some relationship between the other characteristics of the 2 surfaces. And that relationship is as follows. There's K sheets of S2, so there's K things that will look like S2 upstairs. And so this is reflected in the other characteristics. And the second thing, if you're dealing with surfaces with boundary, is that the number of boundary components downstairs, so in S2, this better be less than the number of boundary components in S1. I guess this just follows from some kind of path lifting property. You know, every boundary component needs to have at least one pre-image. Sometimes exactly one, sometimes more. But let's not get too crazy. It can't get too big, right? Because this is a k-sheeted cover. So it can only have at most k pre-images. So these are two things that you need to build a cover. And it turns out this is exactly what you need. You can always do this if you have numbers that satisfy these equations. So there exists a k-sheeted cover. And that's the theorem of Massey. From the 1970s. Okay. So that's great, that's really useful, and knowing things about finite-sheeted covers is good, because then you can start, I mean, you can inherit a lot of tools, I guess. I don't know much about this, but a lot of tools from the more group theoretic world of things like commensurability classes of surfaces, which just inherits the definition of two groups being commensurable. Okay, so that's a great result of Massey, and it uses the finiteness of the surface with this other characteristic, and also uses the compactness as well. So let's just take away both our legs here and try and work out something similar for infinite type surfaces. So these are no longer compact, so they don't have any reasonable definition of another characteristic. And yeah, so let's look at some examples, because maybe people haven't thought about these before. So here's this first one. It's what you get if you just walk in a straight line and you keep gluing tori together one after the other, off in some direction. So there's kind of one way to escape the surface. And because the classification of infinite type surfaces is very hard, we usually give these things fun names. So this is called the Loch Ness Monster. There's another way of drawing this where you can see the humps of the monster. The second one is the second surface. This is called Jacob's Ladder. And this is what you get if you and a friend meet somewhere, and then one of you walks in one direction, one of you walks in a distinct direction, gluing tori together. So there's two ways to escape this surface now. And the correct way of saying this is that the end space of this first one is a single point, and the end space of the second one is 2 points. And so this third, I mean, eventually we run out of names. There's uncountably many infinite type surfaces, so we can't name them all. But I'll name this one because it's going to come up later. So I'll call it Float Monster. Okay, so what happens, how you build this surface is you walk in some direction, and every now and then you glue one of these monsters, one of these Loch Ness monsters, just glue it like a chimney. You're walking past infinitely many chimneys of genus in some direction. So what's the end space here? Well, now you actually pick up some topology. Your end space has some topology. Here it's the natural numbers. There's one end for every natural number for every chimney, and also you can escape the surface by just following the chimneys forever. So there's this extra point at infinity. All the other ends accumulated. So yeah, end spaces can get quite complicated, but there is a classification. And here's a very fast, maybe it's not the most intuitive, but it's a very fast definition of what the end space is. It's basically saying you take some sequence of nested compact subsurfaces, and as they get bigger and bigger and bigger, you look at the complementary regions, the connected components of the complement, and these kind of limit out to what the ends are going to be. Yeah, okay. And so in general, E is a closed subset of the Cantor set, or the Cantor set itself. And yeah, for every single one of these, there exists a surface where this closed subset is the n-space. So things get pretty crazy, and it isn't unique. There's not a unique surface for every closed subset. You can build surfaces in different ways that have, so two surfaces can have the same. Actually, I won't say that. I won't finish that sentence because it'll confuse the next point. The next point is exactly the opposite of what I was going to say. So this is the classification by Caricciarto and Richards. So if we have two surfaces, S1 and S2, which are infinite type, and there are no planar ends, I haven't told you what that means yet, and no boundary, then the end spaces being homeomorphic exactly tells you that the surfaces are homeomorphic. So what are planar ends? Well, a puncture is also an end of a surface. That's kind of a way to escape to infinity. And also you can kind of think about the sequence of compact subsurfaces getting closer and closer, arbitrarily close to a puncture. But there's no genus near a puncture, or rather you can surround a puncture, you can find a subsurface containing that puncture that has no genus. You know, a punctured disk, for example. So that's what's called a planar end. A non-planar end is if every subsurface containing that end contains genus. So all of these things we've just seen, all the ends are non-planar. And for the rest of this talk, bar one other surface, all the ends will be non-planar because it makes things easier to state. So for the purposes of a 25-minute talk, all my ends have genus accumulating to them. Other than that, things can get quite hairy. So, okay, small curves of big surfaces. Let's take a look at what we can do. Here's the first one. And again, just because we're dealing with infinite type surfaces doesn't mean my imagination has improved much. So here's my axis of rotation. Again, and I'll rotate by pi. And yeah, this is a covering space. So it's the ladder covering the monster. And you get this induced map on the end space from this as well. S1, ends of S1 to ends of S2. And the map looks something like this. It's E, the end downstairs, the unique end has two pre-images. So that's pretty cool. You can see the degree of the cover in this induced map, which is useful, but it doesn't always work. So here's another example. So first, let's just focus on this compact thing on the left, the two surfaces, one of genus 2, one of genus 1. And again, I'm just going to insert my, kebab skewer thing here, and then rotate by pi. And so maybe, yes, so this circle is going to have disconnected pre-image like this, and this one is going to have connected pre-image like this. And that's right. That's how this cover works. Okay, that's a good cover, and I'm just going to glue infinitely many of them together, infinitely many of these covers in two directions. And we get this picture, and we get this induced map on the end spaces. And now the surface upstairs has two ends, the surface downstairs has two ends. So our classification tells us this is the same surface, or topologically anyway, even though it looks like one has twice as many genus. 2 times infinity. Okay, so now we don't see the degree of the cover in the induced map. So that's interesting, but there's some kind of covering space like thing happening in this induced map. It would be great if you could say that every cover of infinite type surfaces, every finite type cover induces a cover of the end spaces, but we can't quite say that. Let's zoom out a bit. It's a big surface. back to our float monster, which I've drawn kind of differently. I've drawn it so you can maybe hopefully see the cover I'm thinking of a bit better. As always, there's some axis of rotation that the deck group works with. It's going to spin this whole thing like this. Should I draw some pre-images? No, I shouldn't. Okay. So I don't know, maybe, I don't know if you can keep up with what this cover is doing, but here's the induced map on the end space. I should name the ends, that's what I should do. So let's call this one E0 and this one E1, E2, E3, dot, dot, dot. And the one way out on the right hand side that I can't draw, that's E infinity. And so in this cover, E0 has one pre-image, I'll zoom out even more. It has one pre-image, E1 has two pre-images, E2 has two pre-images. So all the natural numbers, they have ends, they have ends. And so a sequence of ends, and that lifts to the, not lifts, that's not the right word, but it has a pre-image of two distinct sequences, but they both accumulate to the same point upstairs as well, even though they kind of should, you think they should accumulate to distinct points because they're lifting to distinct sequences. So right, the point is crazy things can happen in this induced map on the end space. It's really hard to keep track of. And this is just with one type of end as well. It's all around, genus all around. So our goal was of this work is to look at this induced map and study it and see what we can say, see when it tells us interesting things about the surfaces, but when the surfaces are related. In an ideal world, what it tells us about mapping class groups. There's already some papers of how covers between surfaces tell you things about the mapping class groups, even in infinite type surfaces. And also the other idea was to try and get a Massey type theorem for infinite type surfaces. So just a unique set of data that tells you when a surface can or can't happen. So that's what we got pretty much. We have two closed subsets of the Cantor set, and as long as there is a continuous open surjective map, and it's finite to one, and that finite doesn't get too big, so it's not arbitrarily finite to one. There exists some number such that no point downstairs has more than that many pre-images. So uniformly bounded. So continuous. So what I think is this is like a non-injective homeomorphism, almost. That's what this is. So if you have this is a direct correspondence with there being a finite-sheeted cover of surfaces where the end spaces correspond to the closed subsets. But again, as I said, there's more than one way to have a surface with that end space. So we have to actually build the ends we're talking about here. Sorry, build the surfaces we're talking about. So checking the up direction of this, if and only if, isn't, I mean, there's things to check. You have to check it satisfies all these conditions. The question is, when do you stop, right? I mean, you could probably list a lot more conditions that these induced maps have. But it turned out this was enough to get the other way. So proving the other way, I'll do a very quick example. Okay, so ignore the kind of sausage thing and just look at this map row between two finite sets. X's go to X, Y's go to Y. It's definitely surjective. It's definitely finite to one, uniformly bounded. Isolated points in the Cantor set or in a closed subset of the Cantor set, I should say. They are open subsets. So once you know that, you can convince yourself that this is continuous and open as well. So this is a map, not very exciting, but it satisfies all the criteria we said it should. And then I'm going to draw my cover. So the surface downstairs, it's a surface with infinite genus everywhere and two ends. So that means it's this surface I've drawn. X is out to the left and Y to the right. And now I'm going to build cover. So the way I do this is I'm just going to cover this central compact subsurface first of all. Okay, so you should think, great, good idea. What's the degree? How many sheets is this cover going to have? Well, X has 3 pre-images, so maybe 3 is a good guess. 3 is a good guess. It doesn't always work. It's actually really hard to find the minimum number of sheets that a specific map needs for you to build this cover. But in this case, 3 works. So I build a 3-sheeted cover, and very importantly, I make it a genus 1 surface. And you go back and check with Massey, and he says, yeah, that's fine. You can build a genus 1 surface with 6 primary components. It covers this thing. So it's 3-sheeted. And then I look to the left of the surface. So all of these blue curves here, there's 3 upstairs and 1 downstairs. Oh, my picture's the wrong way around. And so I know that I want 3 ends to project down to 1 end. So I just kind of continue like this, whereas before I took 1 connected 3-sheeted cover. Here I'm going to take 3, yes, 1 disconnected, 3 connected covers. Just 3 things to cover this. But I glue them together and I get 1 connected cover. So that's great. And then I just keep doing this. And I kind of check that all the covering space things work the way they should. And it does. You're just gluing covers together and you're making sure they kind of order. You know, if this was a branch cover, I maybe use the word multiplicity here on these kind of branch points, which are just boundary components. So I don't want these to get out of hand and mismatched and things like that. It's just details to check, but this is the idea. So that's the X's. That's all the X's mapped down to where they should map. The Y's, for one of them I can just do the same. Let's just do that. But the Y's there's only 2 Y's upstairs, not 3. So I can't do the same picture. So what I need to do here is have a connected cover. And this is going to be a 2-sheeted cover. So I have 1 1-sheeted cover and 1 2-sheeted cover that cover this thing. And then I can just continue doing this. So the really important thing here is the genus everywhere is helping us a lot, because it allows you to lift. It allows the lift of a separating curve downstairs, like this one, to include non-separating curves, like these ones. And if you're only dealing with planar surfaces, you just can't have non-separating curves. But this construction really needs them. So that's one of the reasons why we just thought about non-planar ends. Although that's only 1/2 of the paper, the other half deals with planar ends, and it's very complicated. Okay, so that's kind of a rushed example of how we do it. And I'm just going to show one last cover. So this is one I showed at the start, this surface of genus covering a surface without genus. And I'm just going to glue infinitely many of these together in infinitely many directions. So I'm kind of the skeleton of each of these surfaces is like a 4-valent tree. I'm just at every vertex, I'm just gluing a cover, basically. And so now you have a surface with a ridiculous amount of genus, just everywhere, covering a surface with absolutely no genus. These also have names, these surfaces. So yes, so you can have surfaces where genus covers non-genus. You can't have it the other way around. But yeah, there's a lot to keep track of here, this finite world, this finite-sheeted world. Yeah, so I'll stop there, actually. That's a good time. Cheers, thank you.
Okay, thank you for your talk. Does anyone have any questions? I have a tangential question, which is, does this have anything or relate in any way to Thompson's groups stuff?
Oh, it must do, yeah.
Okay.
Let's think. Yeah, I mean, yeah, so there's lots of papers about the relationship between the mapping class groups of, yeah, these kind of surfaces where the end space is a Cantor set, and Thompson's groups. Yeah, so I don't know. Yeah, so one thing I didn't say, so when you think about these commensurability classes here, so that is two surfaces are commensurable or in the same commensurability class. If they either, I think both ways work. If either they cover the same surface finite-sheeted, or they're covered by the same surface, a finite-sheeted way. So it's the same as definition for groups, for surface groups.
Yeah.
Right, and all of these surfaces with a Cantor set of ends belong to the same commensurability class. So,
okay.
Yeah, I mean, I guess this would give you a way of kind of going between these different mapping class groups that all relate to Thompson's group in some way. Because so, yeah, you get these induced maps. So maybe that would be helpful, but I've not thought about it.
Okay. Okay. Does anyone else have any last questions? Okay, well, we should thank Alan again.